Okay, welcome to Math372 Complex Analysis. This is Lecture 11. So what we're going to start today with is a classification of meromorphic functions. Meromorphic functions on the extended complex plane. So we talked a little bit about this one-point compactification, adding this point at infinity. We saw we could draw the plane and the sphere and take what's called the stereographic projection. We're not going to go too much into detail on stuff like this. It's worth being aware that this exists. One of the questions you might ask is, why do we care about these classification theorems? Well, later in the semester, and then if you continue in some other courses, you might get certain circumstances where you can classify the properties your function must have. And then if you have a description of all functions that satisfy those conditions, then you can say, the function I'm looking at must be one of the following. And one of my favorite examples is there's something in modular forms where you're trying to prove certain coefficients have this multiplicative property. And you end up showing that this object lives in a one-dimensional space. Well, a one-dimensional space is spanned by constant multiples of one direction. So it's got to be a constant multiple of a specific function, and then all of a sudden you have the result. So this is a time when the classification incredibly improves itself. I'm not sure if there's a mistake in the proof in the book or a slight omission. So as we're going through this, I will tell you at what point I think we might need to add some small additional result. So we'll start with the theorem. So say f is meromorphic in C and holomorphic at infinity. Then f is a rational function. So that means we can write it as P of z over Q of z.
And P and Q are polynomials.
And P and Q are polynomials. With P, Q, both polynomials in C. So one direction is clear. I could make this an if and only if. If I give you a ratio of two polynomials, then the only poles are going to come from the poles of Q. The only zero is going to come from the zeros of P, except maybe at infinity, and we have to be a little bit careful as to what's going on at infinity. So the interesting direction is to go in the other way, is that if I have something like this, then it's going to look like this. So for instance, if I take the function e to the z or e to the 1 over z, these are not going to be ratios of two rational functions. So they must have slightly different behavior. One of the things we also want to be careful about is things that accumulate. If you have a function that has a sequence of zeros that accumulates, what must be true about that function?
Either it's identically zero or it's not holomorphic.
Either it's identically zero or it's not holomorphic. Good, I forgot to say holomorphic, so yes. So if it accumulates and it's holomorphic, then it has to be identically zero in that open set. When we look over here, we're going to say we want a function that's meromorphic. We're going to basically only want to have finitely many poles. We don't want the poles to be accumulating. If the poles are accumulating, something bad will be happening. Okay? We're also saying that it's holomorphic in a neighborhood of infinity. All right? So the way you should look at this is, not to scale. Here's the complex plane. Here's a circle of large radius r. Everything outside the circle of radius r is going to be my neighborhood of infinity. And if I map this onto the extended sphere, you would think of this as a small little neighborhood, up top over there near infinity. Okay, so proof. Say we have poles at z1 through zn. What would happen if we had infinitely many poles?
This is the direction of rational to the other.
No, this is the direction where we're trying to show that f is a rational function. So in the definition of meromorphic, we want to assume the poles don't accumulate. So whenever we say we have a meromorphic function, we're just going to assume the poles don't accumulate. Okay? Is it possible that you could have an interesting function that has infinitely many poles that accumulate? Perhaps. We're not going to handle that for now. When we say meromorphic, the book defines meromorphic as you have a sequence of poles that don't accumulate. And since we're saying the function is holomorphic at infinity, if I take a small little neighborhood of that, then that means I've got a bounded set that's left over for the complex plane. And I can only have finitely many poles in here, because if I had infinitely many poles in a finite set, it would have to accumulate. You could do this as a Bolzano-Weierstrass if you want, where you could chop it in half, then chop each one in half, and keep doing things like that. Do annular rings, lots of different ways to prove you would have something that accumulates. You could say I have a bounded sequence, and a bounded sequence in a compact set will converge. So we know there's only finitely many poles, so it's very important that we can write it like that. So at each pole, we can write our function f of z as maybe fk of z minus pk of z, where this is going to be a finite polynomial in 1 over z minus zk. That's what it means to have a pole at zk. It has to blow up, and it's going to blow up like 1 over z minus zk. Now we can also look and see what's happening at infinity. How do we study what happens at infinity? So we study the function of f of 1 over z. And so very similarly, and the book will go through the details a little bit more carefully than I'm going to go through right now, we would have something over here minus something over here. Okay, so am I writing this correctly? Is this how I want to be writing it? Yeah. Okay. So I have my function. And I can now study f of z minus the sum k goes from 1 to n of pkz minus p infinity of z. And let's give this function a name. Let's call it g of z. Where do you think the troublesome points are for this function? Where are the points where you have to be careful? So when you look at this function, where are the dangerous points? At the poles. Well, let's see what's going on at zk. If we look at what's going on near zk, this is going to be fine. At zk, this is going to perfectly balance out what's going wrong over here. Oh, I'm sorry, this should probably be a plus sign. These should be plus signs, sorry. Because I want to write it as, something nice plus the part that blows up, something nice plus the part that blows up. So what I'm now looking at over here is if I put in z equals zk, these two parts are going to cancel, and that'll look like fk of zk, which will be nice. And then if I stay away from that specific pole, zk, if I look at all the other ones, these are all going to be nice, because they're distinct zeros. They're distinct numbers in the complex plane. So 1 over zk minus zj, that's going to be fine. So this is not going to have any poles at any of the zk's. What's its behavior going to be like at infinity? Well, similarly, I'm going to subtract off what I need at infinity. When you look at all these different quantities, you're going to have 1 over z minus zk. I want to look at what's going on as z goes to infinity. Is everything going to be fine? Do I have to worry as z goes to infinity about any of these quantities?
The zk's are in that.
The zk's is a finite set of complex numbers. So all these numbers are going to be fine. And so what I claim is that this function has no poles. This function is well behaved as z goes off to infinity. And the reason is as z goes off to infinity, all of these numbers are going to be small as z goes to infinity because it's going to get far away from each zk. The zk's live in some finite region. So there's some giant R where all the zk's are inside here. And so as I go off to infinity, my distance to any of these is going to get very, very large. So the reciprocals is going to be very, very small. The poles have finite order, so there's only finitely many terms. So as long as I stay away, as long as I go off to infinity, everything's going to be fine. And in fact, it's going to be fine everywhere because there's a finite distance between any of the zeros. So if I look inside a circle of radius r, my function has no poles, so it's going to be bounded. So this is using your classic results from real analysis. If you have a continuous function on a closed bounded set, on a compact set, it attains its max and minimum. So the function is bounded in this disk of radius r. Outside the disk of radius r, it's a small neighborhood of infinity. And we're assuming the function is holomorphic there. And so we've subtracted off the behavior, so things should be nice. There's only one thing that somewhat worries me here. Do we have to worry if any of the zk's is actually 0? Because infinity and 0 are in some sense conjugate. 1 over 0 is going to the point infinity. So do we have to worry if one of the zk's is 0? Does this argument break down? So I will leave it to you to go through and look at the proof in the book and see, is there an issue if one of the poles is at 0? Does that affect somehow the argument of how we're approximating things at infinity? We don't need to worry about it for the following. Let's say we have a 0. Let's say the function is 0 at 0, or has a pole at 0. I can just remove that from the function. If it has a pole of order 5, I just pull out a 1 over z to the 5th. And so I just pull out a z to the 5th from my start of q to the z. If it has a 0 of degree 5, I just pull out a z to the 5th from here. I can assume my function is non-zero if I want at 0. So even if it's a concern, we can actually explicitly remove that concern and adjust p and q accordingly. And so the net result is we now have a function which is bounded. G of z is bounded. So what do we know now that we know g of z is bounded? So what must be true? We don't know that yet. What do we know about a bounded holomorphic function defined on all of C?
Oh, it's constant.
It's constant. By Liouville, G is constant. So this whole thing must equal some constant. Each of these is going to be a finite polynomial in 1 over z minus zk. So when we bring all this over to the other side, it's going to get us a rational function. So now, done by algebra. We just get f of z is the sum, k goes from 1 to n, of pk of z plus p infinity of z. Okay. The other thing is, if you want, as I said, you can make the arguments a little bit easier by just explicitly cleaning up the behavior near 0 and infinity. Okay, so this is a classification theorem. It says that if your function is meromorphic on C and holomorphic at infinity, it has to have this form. This turns out to be one of the big deals in complex analysis, trying to classify all the functions that are meromorphic or have certain properties in certain spaces. And as I said at the start of class, the real big success is when you have a space that's one-dimensional. And there is an example of this in number theory we have a space that's one-dimensional, and so the only thing you can do is you can multiply by a constant. And if you normalize the first Taylor coefficient to be 1, then you know exactly which constant it is. Okay. We will do a lot more of this later when we get to the Riemann mapping theorem. And it'll be very interesting to note what kind of automorphisms do we have that map a space back to itself. And it'll be a huge goal to try to classify this. And just to give you a sense of why we care about this and where we're going, how many of you have ever used tables of logarithms? Right, not many of us. When I was in high school, they trained us how to use tables of logarithms. They trained us how to use trig tables. You only need one table of logarithms. And the reason you only need one table of logarithms is the log of x base y is the log of x base b over the log of y base b. This is the change of base formula. And when you're in high school or junior high school, you don't really think that big of a deal. Who cares? The reason this is so important is if you know logarithms in one base, you know logarithms in any base. You only need one table. It's very similar to if you've done probability, you only need the probability of the standard normal. You can convert anything else to that. What we're going to do is we're going to classify all the maps from certain sets to themselves that are holomorphic. And the Riemann mapping theorem will then allow us to transfer that knowledge from simple regions to more complicated ones as to what things look like. This is also a great way to segue into the second part of today's lecture, which is moving to one of my favorite functions, logarithms. Right? So you should have great experience with logarithms. So if I give you a number, we'll do complex logarithms. So let's say I give you z is x plus I, y is r e to the I theta. These are two different ways of writing z. If you need to take a logarithm, which way do you prefer? Second, right? We go to professor school to learn how to ask leading questions, right? Why do we prefer the second?
Because it has an e in it.
It has an e in it.
It's also a product.
Also product. So it has the exponential, which is nice. And when you're thinking about logarithms, e, you'd like to see that. And we know how to take logarithms v. It's also got a product. And one of the big rules we have of logarithms is the log of a product is the sum of the logs. If you can't prove that, rectify it. Learn how to prove it. Look it up online. Talk to me. You should be able to prove that the log of a product is the sum of the logs. I had an English teacher in high school who never called on me, so I got really good at proving log laws and stuff like that in English classes. What do you think is true in the complex plane? What do you think is true about the log of a product? How should we define the log of z? So the log of z is the log of r e to the I theta. And once you leave high school, you learn that log always means natural log base e. We have 10 fingers, but we don't advertise it to the universe. Okay? How should we define the log of r e to the I theta?
Log of r plus I theta.
Okay. Does everybody like that as a definition? Okay, why don't you like that?
It's not a well-defined function.
It's not a well-defined function. So r e to the I theta is the same as r e to the I theta plus 2 pi n. So the problem is I can increase the angle by 2 pi, or integer multiples of 2 pi, and it's the same number. Well, let's fix this. Let's just agree that we will never take an angle that is, do you want to go from minus pi to pi or 0 to 2 pi? Which would you guys like to do?
0 to 2 pi.
0 to 2 pi. Thou shalt not consider angles outside 0 to pi. All right, we'll make it a commandment. All right. All right, well, now we don't have to worry about this, right? Because we're just going to say, well, we just won't do this. I mean, you've seen stuff like this in trig. When you talk about the inverse trig functions and whatnot, they talk about the fundamental regions where they're defined. So the question is, will the log of a product be the sum of the logs? So if we take, for instance, e to the 3 pi I over 2, e to the 3 pi I over 2, what does that equal? E to the 3 pi I, which is e to the pi I. And now if we take logs, we would get pi I over here, because the log of 1 is 0. And over here, we would get 3 pi I over 2 plus 3 pi I over 2 is 3 pi I. So unfortunately, we lose the log of a product is the sum of the logs. There's no way around this. The difficulty is we can't define the logarithm on the entire complex plane. What you normally talk about is you take the complex plane and you take some kind of slit going off to infinity. And you have a region that's simply connected otherwise. And you can define the logarithm, and we'll do this in great detail later, in the remaining part. The most common choice people make for the slit is they throw away the negative axis. You know, they throw away 0 and everything going off to negative infinity. And the reason is if they do this as their definition of logarithm, then the log of a real number reduces to what you've seen before. But we can't define the logarithm on the entire complex plane simultaneously. We can define it on almost all the complex plane. So we can't go all the way around. So if we can't go all the way around, this problem would never happen. Okay, so
even if we don't define it on that slit, couldn't we still think about what would happen if you were off of that and then you, like, by multiplying numbers together, went across it and still had that issue?
Yes, so we would still have that issue.
Okay.
But we're only going to be applying logarithms to numbers in here. So whenever I represent a number, I have to represent it in here. And when I'm traveling, I won't be able to travel around like this.
Okay.
So we will not have, the log of a product is the sum of the logs. We're not going to have that. But as we move around, we never have to worry about continuously moving around and wrapping around the origin. Every time we go around the origin, the angle increases by 2 pi. So we unfortunately will lose the log of a product is the sum of the logs. For those of you who have taken classes with me, you can imagine how crestfallen I am at this point because I love to take logarithms of products. And this is basically telling me my dream is dead. So what do we do? Well, let's go back and think, why do we like logs of products? Convert something that's complicated to something that's simpler. We've seen a little bit right now, but a really good expression in complex analysis is given a function f to study f prime over f. And I'll give you an example of why this is nice. Let's say we have f of z is the sum k goes from n to infinity of an z minus z naught to the end. We have some kind of Taylor series expansion. If n is greater than or equal to 0, if n is greater than 0, we have a 0. If n is less than 0, we have a, this should be a k. So if n is greater than 0, we have a 0. If n is less than 0, we have a pole. If n equals 0, then the function will not vanish. So we can write this as, if you want, an z minus z naught to the n plus an plus 1 z minus z naught to the n plus 1 plus dot dot dot. We can write this as an z minus z naught to the n 1 plus h of z. Well, I'm going to just factor this out. What can you tell me about h of z when z is really, really small? When z is really close to z naught, sorry.
an plus 1 over an.
Well, the first term is going to be an plus 1 over an. So this will equal an plus 1 over an z minus z naught plus an plus 2 over an z minus z naught squared. So what can you tell me about h of z when z is close to z naught? Yeah, so the limit as z goes to z naught of h of z is 0. So this is going to be very, very small. So near z naught, the function f of z looks like an z minus z naught plus a small little bit. Okay? We can take the derivative of f of z. Right? And it turns out that the derivative we're taking here is one of the most fundamental types of derivatives to take. So f of z is an z minus z naught to the n 1 plus h of z. F prime of z is an, and then I'm going to just use the product rule. Product rule, the proof follows exactly as it does in Calc 1. It's going to be n z minus z naught to the n minus 1 1 plus h of z plus z minus z naught to the n h prime of z. We're going to look at f prime of z over f of z. This turns out to be a really good expression to look at. So if we divide this by f of z, the an's cancel. The first term, when we divide by f of z, the 1 plus h of z's cancel. We have a z minus z naught to the n in the bottom, a z minus z naught to the n minus 1 in the top. So the first piece is just n over z minus z naught. The next piece over here, I'm going to get z minus z naught to the n cancels that. The an's cancel. I'll get h prime of z over 1 plus h of z. What kind of function is this near z naught? Holomorphic. So this is holomorphic near z naught. And now you can see why I wanted to note that h is near 0 when z is close to z naught. I don't have to worry about dividing by. This is our favorite function to integrate. It's just 1 over z minus z naught. If I integrate it around z naught, I'm going to just get 2 pi I times n. And so what's fascinating about this is notice that the coefficient an doesn't matter. When you look at f prime over f, the coefficient does not matter. All that matters is the order of the 0 or the pole. And in fact, if there is no 0 pole, if the function is non-zero, then n would be 0, this term would vanish, and you would just have a nice holomorphic thing. Okay, why do we care about something like this? Well, let's go back to logarithms. We wanted the log of a product as the sum of the logs. That's gone, but something close to that actually survives. So consider g of z is f1 of z, f2 of z. G prime of z is going to be f1 prime of z, f2 of z, plus f1 of z, f2 prime of z. G prime of z over g of z, well, if I now divide this by g of z, the f2's cancel here, and I get f1 prime of z over f1 of z, plus similarly f2 prime of z Anybody notice what kind of derivative this is? At least formally.
It's like dx over x, with log x.
Close, very close. It's like d by dz of log of g of z. And I'll put this in quotes. So this is often called the logarithmic derivative. If you are ever unsure about what to do in complex analysis, take a logarithmic derivative and do a contour integral. When in doubt, that's a really good thing to do. And what this tells us is the logarithmic derivative of a product is the sum of the logarithmic derivatives. So the logarithmic derivative of a product is the sum of the logarithmic derivatives.
Why is that a logarithmic?
Well, if you take the derivative of log of g, you get 1 over g times g prime. Right? So this looks like the derivative of log g. We can't say that yet because we haven't really defined what the complex logarithm is. But at least it looks like the derivative of the log. So this is a new operation. Logarithm has some issues, but logarithmic derivative is much better behaved. And this is a graduate level class, so standard logarithm rules shouldn't suffice for us. We should have new exciting things. So instead of rules about logarithms, we now have rules of the logarithmic derivative. Okay? So this is a pretty good result. Think of it as, if I want to try to understand a function, it's nice to break it down into different pieces and multiply them together. Think of it almost like primes and decompositions. And what we saw over here on the other board, this was meant to be like a little motivation, that near a zero or a pole, I pull out the highest term. I pull out the action. And then what's left over is nice. So much of your life is action plus leftover bit that's nice. This part is harmless to integrate. It's holomorphic. I can integrate a holomorphic function over any contour I want. What's it going to be? 0. And if I had to choose a non-holomorphic function, I would choose the 1 over function. It's the simplest one. We know how to integrate it. So it looks like this should be telling us something. Okay? So are people happy with the notion of the logarithmic derivative? So I'm going to now isolate a result about the logarithmic derivative. So I will call it the argument principle. So f is holomorphic on open omega, no zeros on a curve gamma, then 1 over 2 pi I integral over gamma of f prime of z over f of z dz is equal to number of zeros of f inside gamma minus the number of poles of f inside gamma. Why don't I have to worry about the zeros or poles on gamma? Actually, instead of saying holomorphic, let's do meromorphic. If I say holomorphic, there's no zeros. It's still true, but it's a little bit stronger. So we're assuming that there are no zeros or poles on gamma, so I don't really have to worry about zeros or poles on gamma by assumption. Since we're assuming it's meromorphic, part of the definition of meromorphic is that your poles don't accumulate, so there can only be finitely many. Could we have infinitely many zeros inside omega?
Well, it would be identically 0.
It would be identically 0. So if I looked at this theorem and if I chose f to be the 0 function, what would happen? I would have the derivative of 0 of things could blow up. So if you want, assume f is not identically 0. Right? If f is identically 0, okay, maybe things break down. We will assume we do not have the identically 0 function. The proof of this is really straightforward once we have the logarithmic derivative. We have our expansion here. Near any 0 or pole, this is what f looks like.
So maybe this just works out, but it looks like there's an integral times 1 over 2 pi I set equal to an integer?
Yes.
Okay.
Yes. And in fact, there's going to be enormous consequences of this. What can you tell me about a integer valued function that's continuous? Yes. So this is going to be, we're going to go back to the tactical nuclear attack. Okay? Once you have a continuous function that's integer valued, there is a lot you can deduce about it because it has to be constant. Okay? It is amazing what we can do with this. So the proof, I'm going to just sketch the details. It's the same proof we keep doing every single time. Enumerate all the places where the function has a pole or a 0. Draw little things coming out like this, going around clockwise and coming back. Do this at each one of these. You then take the limit as the thickness goes to 0, so all these cancel, and now you get that 1 over 2 pi I integral over gamma of f prime of z over f of z dz is equal to 1 over 2 pi I, the integral, we'll call it over gamma k, and we'll do a sum, k goes from 1 to n, of f prime of z over f of z dz, where we'll call gamma k the circle about each of these. Well, from what we've done over here, near zk, f prime of z over f of z is, I'll write it n sub k for the order of the 0 pole there, over z minus zk plus something that's holomorphic. And so now when I do the integral, so 1 over 2 pi I integral over gamma k of f prime of z over f of z dz, when I integrate this piece, I'm just going to get nk. And when I integrate that piece, I'm just going to get 0. And that's the proof. So this is the argument principle. If you integrate f prime over f, you count the number of zeros and you subtract off the number of poles. If you have a 0 of multiplicity 4, you count that 0 4 times. If you have a pole of multiplicity 3, bless you, you count that 3 times. Okay? So the question is, who cares? Why would we want to count the number of zeros or the number of poles? Okay? It's maybe somewhat interesting, but why would we care? Now, the other thing is, if I change the curve a little bit, am I going to change the number of zeros or poles inside? So this is going to be a continuous function of, in some sense, of the curve gamma. And as I change the curve a little bit, it's going to stay here, constant. All right, I'm not quite sure exactly what it means to be a function of gamma, but... So there are 3 big consequences of the argument principle. Has everybody written this down? Because I'd like to keep the statement of the argument principle on the board and write the consequences. Has everybody written this down? Okay. So there are 3 consequences of this. And then whenever you get a result in complex analysis, what should you compare it to? Real analysis. So the first and these are good consequences, is Rouche's theorem. Say f is holomorphic on an open omega, so is g and the absolute value of f of z is greater than, strictly greater than the absolute value of g of z on a curve gamma inside omega, then the number of zeros of f inside gamma equals the number of zeros of f plus g inside omega. You've got to be a little bit careful which book you use. Some books talk about f and f plus g. Some books talk about f and g. And in those books, g is basically equal to f minus something. It's basically the same. The best description I know about this, and I think this one might even be on Wikipedia, is this is the walking dog theorem around a pole. If you have a pole here, and you're walking in a giant path, and you're holding a dog on a leash, and the leash is so small that the distance of the leash is always strictly less than the distance you are to the origin, however many times you walk around the origin is equal to the number of times the dog walks around as you drag the dog. The dog can be doing anything you want, but you're going to be dragged around. It's going to walk around the same number of times. In particular, notice as soon as I write this, you know something about the values of f on the curve gamma. What do you know about f on gamma? Note, on gamma, we have the following. What must be true about f? Bounded from below. So we have f is non-zero. Excellent. Because it's strictly greater than g of z in absolute value. Smallest g of z can be a 0, so f can't vanish on the boundary. So whenever we're applying this limit, we want to apply it in a situation where f is not 0. Okay, that's one. The second is the maximum modulus. A holomorphic function takes its maximum absolute value on the boundary. So if I look at my values of absolute value of f inside gamma and on gamma, it's got to have its largest value on the boundary. Could it also have its largest value inside the boundary? Yes. Function could be identically constant. And it might be an interesting question, what would it mean if it takes its maximum value both inside and on the boundary? And then the third is the open mapping theorem. F holomorphic on an open U, then FU is open. So the holomorphic image of an open set is open. Okay, these are three phenomenally important theorems. And so what I wanted to do is state them today so that they're percolating. So that for the next 2 days, as you're just wondering, oh, it can't be, these things can't be right. Think about analogs. Think about nice real functions. Do they map open sets to open sets? No. Something's going on here. Okay, so again, as always, the question is, who gives a damn? Right? We've got 5 minutes left. Let's look at consequences of Rouche's theorem. Why Rouche walks. If you had to choose one theorem from algebra to ponder on a desert island, what would you choose? One theorem from algebra. The fundamental theorem of algebra, right? I remember years ago I was at a lunch with Phi Beta Kappa and President Falk, and we were asked if we could have one movie to watch on a desert island, what would we choose? And I wanted to make sure before I answered it, it's not my favorite movie, it's which movie could I watch again and again and again? I said yes, Fever Pitch. I can watch the Red Sox coming back against the Yankees every day and still smile. Right? Fundamental theorem of algebra, that is our greatest theorem in algebra. A polynomial of degree n has n roots. Can anybody give me a polynomial where it's really easy to prove that it has n roots? Z? Can you be a little bit more general? I want n roots. Z to the n. So for instance, we could take f of z is an z to the n has n roots. Okay. Now we have by Rouche that if f of z is strictly greater than g of z inside a curve, then f and f plus g have the same. So let's let some polynomial p of z be an z to the n plus an minus 1 z to the n minus 1 plus a0. We want to prove that this has n roots. Here's our function f. Here's our function p. Anybody want to give me a guess for what g of z should be? Yeah. P of z minus f of z, an minus 1, z to the n minus 1, plus a0. If z is sufficiently large, will f of z be greater than g of z in absolute value? This is growing like, say z has absolute value r. This is going like a constant r to the n minus 1. So if absolute value of z equals r is, trying to get excited. If it's big, okay, how big can this be? The absolute value of p of z is going to be at most, we have n terms, the maximum 0 less than equal to k less than equal to n minus 1 absolute value of ak times r to the n minus 1. And this will be strictly less than the absolute value of f of z. So if we choose r sufficiently large, then g of z will be less than f of z on a circle of radius r. So by Rouche, f and f plus g, also known as p, have the same number of zeros. If I give you a polynomial of degree n, could it have n plus 1 zeros? No, every time I have a zero, I can just factor it out. I know I don't have more than n zeros. I'm not worried about that. I just need to show that it does have n zeros. We just proved the fundamental theorem of algebra in less than 5 minutes. Without using Liouville's theorem. Without using the fact that a holomorphic function that's entire and bounded is constant. This is, complex 2. Second proof. Any result that's really good, you want multiple proofs. Depending on your mood, depending on what you're doing, different things will generalize better, different things will illuminate better. This should give you a sense of the power of this theorem. It should also remind you that we haven't yet proven Rouche's theorem, and probably should get to that at some point. But at least we're now motivated for the proof of Rouche's theorem. As a really nice consequence of Rouche, we have the fundamental theorem of algebra. So, Gauss was very proud of something called quadratic reciprocity. I think at the end of his life, he had 8 different proofs of it. He collected proofs of this great result. Certain math results have a lot of proofs. If you had to guess, which result do you think has the most proofs? Probably Pythagorean theorem. I mean, if I had to guess, I would say Pythagorean theorem has the most. Any other thoughts as to what would probably be pretty high on the list? Infinitude of primes, that's also pretty high. Maybe square roots of certain numbers is pretty high. Fundamental theorems, if you can find multiple proofs of them, that's phenomenal. There is the multivariable calculus proof of this. I'm sure there's probably an algebraic proof. I haven't really gone far enough in algebra to know that. I love these analytic proofs and trying to get a sense of what's going on and think about the consequences. All right. What's really looking on, we're going to see at some point, is integer valued continuous functions are very well known. And we're going to just try to exploit as much as we can out of integer valued continuous functions. If I listed that as the title of this course, I might not be allowed by the registrar to offer a class on this. I have had an issue with the registrar in the past over names of one of my courses, but I was able to triumph in the end. All right, this is probably a good time to end.